Okay. Hi Precalc class. Today we had a rushed and not super great, but maybe fine, lesson on the Binomial Theorem. It's just like a 10-minute follow-up. Hopefully it will really be that short. Okay, we were working our way through this packet, and we basically got all the way through understanding the Binomial Theorem, but we didn't get to do any practice. So, some practice. What's the coefficient of the a to the fourth b to the seventh term in the expansion of a plus b to the 11th? Okay, so this is the kind of question that we didn't know how to answer at the beginning of class, but when I expand out a plus b to the 11th, I'm going to get to 12 terms. They are going to be of the form like, you know, a to the fourth, and a to the 11th, I mean, and then there's going to be a term which is a to the 10th, b, and there's going to be a term which is a to the 9th, b squared, you know, etc. And what we learned in class was how to compute these coefficients. So this just asks for one of them. What is the coefficient of a to the fourth, b to the 7th? Okay, and alright, once you know the answer, then you just know the answer. But the way I encouraged you to think about this is to imagine this entire tree, that starts with 1, and this is AB, and this is A squared, AB, this is also AB, this is B squared, and every row of the tree, you go all the way down, multiplying by A, each term by A, and each term by B, each row of the tree. The number of terms doubles, and if you don't combine like terms as you go, by the time you get all the way down to the 11th row of this tree, we're going to have 2 to the 11th, so 2048 individual terms, and each of them has depth 11, so each of them will have exponents which add to 11, so that's kind of an explanation of that also. And okay, so here we are, a to the fourth, b to the 7th. Will be one of the combinations which comes up. And so the answer to what's this coefficient, I would like you to think of as the answer to a counting problem. Let's count the number of times that a to the fourth, b to the 7th shows up down here in the 11th row of this tree. And the way we did this in class was to count the paths by not combining like terms as we go, and by maintaining the tree structure. Then it becomes clear that every distinct leaf in the tree has a unique path leading to it from the root of the tree, which is 1, the empty product. And okay, so how many paths through this tree are there that terminate in a to the fourth, b to the 7th? I'm kind of re-explaining and re-teaching the Binomial Theorem as I go over this. Answer, well, in every one of those paths, you chose A 4 times and B 7 times. You end up with an a to the fourth, b to the 7th by constructing some path in which of your 11 choices, you went right 7 of those choices. And so this is now a counting problem. If you think 4, 5, 6, 7, 8, 9, 10, 11, if you think of the 11 choices about whether to go left or right, that is, whether to multiply by A or B, as being maybe like a string of length 11, then the question is, how many ways are there for precisely 7 of those to be right? So the answer is that there are, and now I just give the answer to the problem, 11 choose 7 ways in your 11 choices to choose 7 of them, to designate 7 of them to be go right choices. Which is to say, you had 11 choices about whether to multiply by A or B, and if you chose to multiply by B in 7 out of those 11 choices, then you end up with a to the fourth, b to the 7th. And since there are, since we're sort of by keeping the entire tree in our minds, we are sort of caring about the order, so to speak, in which you multiply by a and b. Of course, when you combine like terms, because multiplication is commutative and associative, you merge them all together. But by keeping the tree, you can actually trace the sort of order in which that a to the fourth, b to the seventh term was created, the order of the multiplications. And that's what's being kind of represented here. Okay, I have now used up 5 of my promised 10 minutes by just reteaching the binomial theorem, but hopefully everyone understands this now. Yeah, good. What is 11 choose 7? Well, it's 11 factorial over 7 factorial 4 factorial, and sometimes I do these and sometimes I don't, depending on my mood. It's 11 times 10 times 9 times 8. The 7 factorial is going to cancel the rest of them, over 4 times 3 times 2. The 4 times 2 cancels the 8, so we get 3. And so that's 33 times 10, so it's 330. So you know what, it really just wasn't that bad. And the answer is that that we're going to have that the coefficient is going to be 330. And that's just one of the 12 terms in the expansion of a plus b to the 11th. Okay, number 2, now we'll just kind of do the problem a little bit more quickly, but maybe this problem is, slightly harder or something for some people. What's the coefficient of the x cubed y to the 8th term in the expansion of 3x plus 2y to the 7th? Okay, so to do this problem, you just have to, be sophisticated or whatever, and realize that, 3x is like a, essentially, and is this even the right problem? No. This should be a squared here. That's what it says in the packet, so that's what I meant to write on the board. Okay, so that means that a is 3x, and b, so to speak, is 2y squared. Okay, and that whole thing is being raised to the 7th, and so when you do this expansion, what do you get? This is like the first term is going to be a to the 7th, so to speak. So that's like 3x to the 7th, and then the next term is going to be 7 choose 1, which is just 7 times 3x to the 6th times 2y squared, etc. Okay, so that kind of gives you the gist of it. So when am I going to get an x cubed y to the 8th term? Well, the only way that's going to happen is if 3x is being cubed and 2y squared is being raised to the 4th power. So I don't know, maybe I don't need to go into any sort of explanation of why I know that, but maybe I do. I don't know. But when you expand this out, one of the things that you get in this expansion is going to be a term that resulted from raising 3x to the 3rd and 2y squared to the 4th. And what is the coefficient going to be? Well, once again, I'm on level 7 deep of the tree, so the number of times in which this term appears is when I chose to go right 4 out of my 7 times. So that's 7 choose 4. Okay, but if someone wants you to actually compute this coefficient, what is 7 choose 4? It's 7 factorial over 4 factorial, 3 factorial. I think this one even came up in class. This is 7 times 6 times 5 over 3 times 2, so it's just 35. But we have to be kind of careful. If we want to know what this actual coefficient is, it's going to be 35 times 3x quantity cubed is going to produce like another 27. And so maybe I'll even write 27x cubed times 2y squared raised to the 4th power is going to give me 16y to the 8th. And so the final answer is just like whatever 35 times 27 times 16 is. I don't feel particularly like I need to do that right now, but maybe you do feel like you need to, so go for it. But anyway, that's kind of the answer. So just be aware that if the binomial is something more complicated than a plus b, then you just need to sort of be careful and take that into account. Maybe that's kind of obvious. Okay, good. So you can just turn this off now, or you can keep watching. I guess I encourage you to keep watching. I'm just going to quickly sort of resolve that one thing that didn't come up in class, which is, so I guess here's what we did. We expanded a bunch of binomials. We sort of pulled out of nowhere this object called Pascal's triangle, which we didn't really explain at all. And you know, what is Pascal's triangle? It's just this thing which you can make by performing this recursive rule, which is to say you add the parents. So you shift over slightly, 1 plus 2 is 3, 2 plus 1 is 3, and so you add the parents. Okay, so, everyone understands what this means, I hope, but right, these numbers always add up to be the number beneath them. Okay, so that's cool and all, and we observed that the numbers in the rows of Pascal's triangle are the binomial coefficients. But then, failing to understand that, we pushed on and discovered that the coefficients of in the expansion of the binomial can be expressed using the combination notation, using a sort of counting principle, because it's really a counting problem. So the final thing that we didn't get to was to bring it back to Pascal's triangle. What does this have to do with Pascal's triangle? Well, let's try to explain. This time I'm also going to draw a tree, but this time when I draw the tree, I am going to combine like terms. So here I have A and B. Once again, I don't even think I need to write it now, right? By default, I let multiplying by A mean go left and multiplying by B mean going right. And okay, now I'm going to, you know, add in another row. So multiplying by A gives me A squared, by B gives me AB, by multiplying B by A gives me AB, and multiplying B by B gives me B squared. So far this is exactly what we did in class. But now, I shall introduce a new step. And the new step is combining the like terms. The very thing that I said last time led to us missing the point. This time I'm now recommending. So combine the like terms. Bring these together and write this as 2AB. Okay, well that's looking a little bit more kind of recognizable now. And this is in fact the expansion of A plus B squared. Okay, we continue. So, ja. Okay, this is looking like a pretty terrible tree. What's happening here is A cubed. What's happening here is, aha! When I multiply A squared by B, I get A squared B. When I multiply A by 2AB, I get 2A squared B. Here, when I multiply 2AB by B, I get 2AB squared. But here, when I multiply B squared by A, I get AB squared. And here I'll just get B cubed. Okay, so now I combine like terms again. So here I have an A squared B, and here I also have an A squared B. Okay, well this is going to just keep happening because, now first let me just do it. Or maybe I talk about it first. This is just going to keep happening because I've combined like terms in the previous line, it means that these two, well, maybe I need to go one more level to really see what's going on. But okay, here I also combine like terms. Okay, let's just go one more level and then kind of wrap it up. So here I get A to the fourth. Here I get, this is going to work out fine, cha. Okay, so what do I get? A to the fourth. Here, and I'll talk it out as I go, I guess, is the thing to do. Here, what am I doing? I'm multiplying A cubed by B. And I'm multiplying 3A squared by A. But of course, because I combined like terms in this previous step, in fact, these two are always going to differ by 1 in the exponent of A, and also by 1 in the exponent of B. In other words, if I multiply this one by B, then it's going to have one more B in it than it did already. In other words, it's going to have the same number of B's as this one. But then I'm multiplying this one by A, but this one had one fewer A than here. Okay, so in other words, if comparing any two numbers in the tree this has one more a than this does, and this has one more b than this does, then by multiplying this one by b and this one by a, I make them the same. Okay, so these two are always, it's not a coincidence that these two are going to fuse like that. They're always going to fuse like that, because multiplying a cubed by b and multiplying 3a squared by a is going to bring the number of a's and b's the same, to be the same. And of course, because I'm multiplying 3a squared b by a, that's going to give me 3a squared b, but another a cubed b. I'm multiplying 3a squared b by a, so it's giving me 3a cubed b, and now I have another a cubed b, giving me in total 4a cubed b. Okay, and that just keeps happening, right? These two, this one's always going to have one more a than this does, so but here we multiply by a, bringing the a count to be the same. This one is going to have one fewer b than this does, but then I multiply by b. So as I generate the next row of the tree, by multiplying everything through by a, multiplying everything through by b, and adding the result, terms which are right next to each other are going to meet in the middle, and in fact we're going to get 3 of these and 3 of these, so that becomes 6 a squared b squared. In other words, and okay, let's just finish this off. I have 3ab squareds, but I multiply by a, and so the end result here is going to be I multiply by b, so it's going to be ab cubed. And how many of these ab cubes do I get? I get 3 from here and 1 from there, and the answer is therefore 4 total. Okay, and so now we get a different perspective on these coefficients. Why, on some sort of deep level, you know, why is this 6 or something like that? Well, it's 6 because the only way to make an a squared b term out of a term whose degree is 3 is to either multiply an a squared b term by b or an a b squared term by a. And I have 3 of those and 3 of those. And so I end up with 6 a squared b squared terms because I had 3 of these and 3 of these. Similarly, I end up with 4 a cubed b terms because the number of a cubed b terms in a plus b to the 4th is just going to be the number of a cubed terms, which get multiplied by b, plus the number of a squared b terms, which get multiplied by a. Okay, and therefore, this is what Pascal's triangle has to do with the binomial theorem. Here I'm just making Pascal's triangle right before you. What was the recursive rule which enabled us to sort of mindlessly generate the next row of Pascal's triangle? The recursive rule was add the parents, right? I add 1 and 4 to get 5. I add 4 and 6 to get 10. I add 6 and 4 to get 10. I add 4 and 1 to get 5. It's so easy. It encourages you to just do it mindlessly without thinking about it. But what does it mean, man? Well, what it means is to get 5a to the 4th b is just 1 plus 4. Because so I add 1 and 4, here I'm adding 1 and 4, because the number of these is just the number of those plus the number of those. And when I want to know the number of a cubed b squared terms in a plus b to the 5th, well, the only way to make an a cubed b squared term is to find an a cubed b term and multiply it by b, and there are 4 of those, or to find an a squared b squared term and multiply it by a, and there are 6 of those. Thus, there will be 10 a cubed b squared terms. And so, okay, that sort of completes the explanation. And the final thing I'll say is, in fact, what we've actually shown now, this is sort of now a proof that Pascal's triangle does count the binomial coefficients. That's my feeling on the matter. I have proven to you that these are the correct coefficients in the binomial expansion, and by doing this proof, I have sort of discovered, had I never heard of it before, I kind of just discovered Pascal's triangle on the spot. It's a triangle of numbers that results from sort of adding the parents, but this time kind of with meaning. And therefore, the numbers of Pascal's triangle can be conceived of differently. These are, in fact, it's just a triangle of binomial coefficients. What's sitting at the top? 0 choose 0, which is 1. What's next? 1 choose 0, and 1 choose 1. How many ways are there given one object of choosing none of them? One way. How many ways are there given one object of choosing one of them? One way. And this is 2 choose 0, 2 choose 1, which is 2, 2 choose 2, which is always 1, 3 choose 0, etc. So this is kind of like the big kid way of talking about Pascal's triangle. The numbers in Pascal's triangle themselves just are answers to counting problems. These are called the binomial coefficients, or they're called, this is just numbers written in combinatorial notation. There are lots of different names for them. Okay, good. I totally lied. That was probably like 20 minutes. Goodbye, though.